Most assume our vision works like a high-definition video camera, that we open our eyes and a lens smoothly records the world around us in a continuous, unbroken feed. However, the physical mechanics of the human eye contradict that experience entirely. Instead of panning fluidly across a room, our eyes move in erratic, violent jerks called saccades. These jumps happen 3 to 4 times every second. During these movements, the eye rotates so fast that the incoming light becomes a useless smear. Then there are the blinks. Every few seconds, we physically shut our eyelids, cutting off the intake of light to the retina completely. If we relied on this raw data alone, our conscious visual reality would look like a chaotic, disorienting strobe light flashing in the dark, rather than a coherent world. Adding up every saccade and blink, we spend up to 20% of our waking hours receiving no visual information. To prevent a motion-blurred mess, the brain shuts down processing during eye movements. It cuts the feed, then stitches the remaining fragments together. This raises a biological mystery. How does the brain bridge these massive gaps to create the feeling of a seamless reality? The answer is a highly advanced biological buffering system that works behind the scenes to smooth over the constant interruptions. Without this buffer, we would lose our sense of spatial continuity. Navigating a room would feel like trying to find your way in a dark house using only a flickering, failing flashlight. Every fragment of light that reaches the eye travels to the visual cortex. Once there, the brain divides the data into 2 parallel processing streams to handle different aspects simultaneously. The lower path, the ventral stream, focuses on identification, recognizing what an object is. The upper path, the dorsal stream, is the spatial mapper, tracking where an object is in 3D space. Identifying the complex geometry of objects while simultaneously calculating its velocity requires a massive coordinated neural spike. This coordination isn't instant. The brain must sync these separate feeds, a process introducing a slight but measurable time delay between the moment light hits the eye and when we become aware of it. To keep the what and the where in sync despite the constant gaps from blinking, the brain requires a short-term memory buffer to hold the data steady. This specific biological buffer is known as iconic memory. Iconic memory acts as a neurological visual echo, holding on to an image for a few hundred milliseconds after it has physically disappeared from view. The brain uses this lingering echo to bridge the dark intervals created by eye movements, ensuring the world doesn't vanish every time we blink. The system is also predictive. It uses the trajectory of the visual echo to anticipate where an object will be next, painting that prediction over our blind spots. This means our feeling of continuous time is a carefully constructed illusion, a bridge made of echoes to hide the physical gaps in our biology. This visual echo is what makes high-speed reactions possible. Catching a fast-moving object requires the brain to track a trajectory that your eyes are physically too slow to follow in real time. Whether we are driving a car or simply reading a sentence, we are relying on the brain's ability to predict reality rather than passively recording it. Because the entire cycle of dual-stream processing and buffering takes a measurable amount of time to complete, our conscious experience of the world always trails behind the physical world. Ultimately, what we call reality is an active hallucination of the immediate past, smoothly orchestrated by the echoes of the visual stream.